Ready to go. Let's get started. Got an exam on Thursday. I'll try to go through what I think are the highlights for you to go over with regard to the exam. I'll be sure that the lecture and the notes are up this afternoon. You can review them if you want. What we've gone over since the last exam includes the solution of ODEs, Gauss quadrature. Although you may look back, we covered integration on the first exam, except Gauss quadrature. That's important that you be able to do a Gauss quadrature. Then the Monte Carlo method, of course we talked about that, the random number generator. The solution of partial differential equations. And then the finite difference method, and we talked just briefly about the finite volume method. Just be sure you know the difference, but be sure you understand the finite difference method. The last is ADI, alternating direction implicit. We'll actually go over that at the end of the slides. And SOR, remember what SOR stands for? Okay, an iteration. Ordinary differential equations, the most common ODE methods. These are the two. Euler method. Be sure that you can do a simple Euler method. The other, Runge-Kutta. Now, you don't want to have to do a fourth order during an exam. So at least understand that you can do a second order. Now, how many kinds of second orders are there? There's a whole bunch of them. Find one that you're comfortable with and that it's easy for you to remember or to use. First order ODE, that's generally the types of problems that you're dealing with in these kinds of solutions. You can solve second order. My guess is if I look at the exam, I'll probably give you a first order, but might change my mind between now and Thursday. But also take a look at a second order as well. Second order ODE looks something like this. What you can do is fake it out, and you can reduce it to something that looks like a first order. So it's a two-step process. You actually did this on one of the homework problems, if you remember. So that's how you can get around that. You can change that form of that equation to something that looks like this, where it looks like a first order differential equation, and then you can solve it simply as an Euler technique. So here's what you're doing with regards to Euler's method. You have a differential equation, you just set it y, I plus 1 equal y, I plus phi h. By the way, what is this reminiscent of? A one-sided finite difference, which comes from Taylor series. Right? So if you can remember that, you've got it made. So basically, what you're doing is solving for the phi, which is a function of whatever the steps are that you're doing with regards to the iteration. You wind up with that simple little algorithm. Here's an example. I think we went over this before, but just in case, we'll do it again. Here is y prime equal to 4e to the 0.8t minus 0.5y. We're going from 0 to 4t to the time step of 1. There's the initial condition, y equal 2 and t equals 0. So here's the Euler method. You just plug in the values. What you're doing is solving for the function at 0 and 2. You get 3. So in the first step, y1 equal 2 plus 3 times 1 equal 5. That's if you wanted to compare with the true solution. So what you're going to do is just keep doing these until you say, oh, that's at least the accurate answer, or it's close enough, or however many steps I tell you to do. Second step, you just bring this value down, put it in right here. You evaluate the function at 1 and 5. Plug in, you now get 11.4. So you can see, in this case, what's going on? Looks like it's trying to diverge. So maybe our step was too big. I won't give you a trick problem like that. But this is just to show you the process as to what you do. Just review that. Be sure that you understand that. Now, second order Runge-Kutta. This is the one that I really want you to remember. I mean, you've done a fourth order with regards to the homework, so it takes a little time. But on this one, you should be able to do it as a problem. It shouldn't take too long. Like I say, you're going to have to define what you want to use with regards to your preferred second order method. Kuhn's method is one where you've got a half and a half. or sometimes you can have a 0 and 1 or whatever, just depends. Just pick one out that you can go through that will be second order. It won't take a long time to try to calculate, and it's good enough as far as a demonstration of the technique. Here's the one this is the one I generally tend to use, but like I say, you can use others. Here's one. I've used the midpoint method as well. You see how simple this is. So you don't have to worry about what these coefficients are when you plug them in, right into here. So you just throw them in and away you go. So I would suggest probably one or the other of those, but you may have one that's just as good that you're comfortable with. Now with regards to Gauss quadrature, this is the preferred integration technique, and it's what the commercial codes tend to use, particularly when you start getting into methods involving finite elements or so forth. There are various kinds of Gauss quadrature. And in general, what you're doing is establishing these sets of coefficients that are going to create what are called weights and Gauss points. And so there's a table of weights and Gauss points. In this particular case, this is setting up for the first level of Gauss points, and it turns out in the simplest linear approximation, you have 2 points, minus 1 over the square root of 3 and 1 over the square root of 3. So that's the 2-point Gauss-Legendre formula. So what it means is that the integral that you have can be evaluated using these 2 Gauss points. It turns out that the weights associated with those Gauss points are 1. So you plug in the function evaluated at that Gauss point, the minus 1 over the square root of 3, plus the value at 1 over the square root of 3. Turns out that's third order accurate. Remember, this is important. Limits of integration are changed from minus 1 to 1. So I give you a problem that says evaluate this integral from 0 to 2, or what have you. What are you going to have to do? First thing you do, change the limits of integration. It must go from minus 1 to 1. This is what's going on. If I evaluated the points at these corners right here, those 2 points, what would that method be called? Starts with a T. Trapezoidal rule. So what the Gauss quadrature is doing is it's kind of coming up with these 2 points within that approximation where it's saying, okay, I'm going to balance out the error. That's positive here, that's an overshoot here, and so it turns out that it's a very, very accurate method. Change of limits. All right, if you can't remember how to do that, here's what goes on. Basically, here's the little formula. This is the one that you ought to use. And it's easy to remember. So if you know what the limits of the integration are, B and A, then you can plug it into the relationship, and you'll get X that's converted to XDs now, or size, or whatever the variable is that you want to use. But don't forget that you also have to change the dx to whatever that would be in terms of the new variable. Now, if I want to use higher formulas, then all I'm doing is using more terms. So I can go out to n as many as I want on this. It just takes a lot more time to compute. Generally, the most accurate are typically done around 3 Gauss points. Here's an example. Use Gauss quadrature to evaluate this function, 0.2, 25x, 2x, 2x squared, so forth and so on. We're going from 0 to 0.8. First thing you do, change the variable so that the limits go from minus 1 to 1. So we just plug it into the formula. Here's what our new x looks like. Here's what the dx looks like. So here is the original equation, our formula. That is then changed. Notice limits are now minus 1 to 1. Wherever I have an x, it gets replaced by this. So right there, right there, right there, right there, right there. And then that dx now becomes 0.4 dx. Now if I'm using 2-point quadrature, I just plug in the values wherever I have these things. I plug in minus 1 over the square root of 3, and then I do it again for 1 over the square root of 3. So here's the value that I would get for this integral. for the minus 1 over square root of 3, and then the positive, I get 1.8. So it's doing all right. That's just a very simple approximation. Does everybody understand this? Can you do this? These are the table of Gauss points. So, and if I give you a problem like this on the exam, I will give you the table. You can't memorize this stuff, so don't waste your time. So here would be using 2 Gauss points. You notice the weights are 1. That's the same as 1 over the square root of 3. If I'm using 3 Gauss points, that's what this would be. If I use 4, if I use 5, and so forth. And you can go on up. Look at the order of accuracy that you get. All right, now, okay, Shalene, you can, what I want is sitting here and here, and you're evaluating whatever that function would be at each of these Gauss points. What you wind up with is around 1.64. Okay?
That 0.4 plus that point, the part where we change the limits of integration still stays in there. Right?
Yep.
Okay.
Well, it sure does.
That's what
Everybody comfortable with doing a Gauss quadrature?
No, I didn't.
Least squares. Let's talk about least squares. You just did that as a homework problem. What we're doing here is a regression approach. There, you can do a linear, quadratic, cubic, the higher orders. Really doesn't matter. The problem that I will give you will probably be relatively simple. I may ask you to say, gee, is it linear or is it quadratic? I'm not sure. Depends on the points and how they scatter. My recommendation in doing these kinds of problems is always take the data first, do a rough plot. Gives you kind of a ballpark idea as to what to expect. With regards to fitting a best line through the data points, what we're doing is really minimizing the sum of the residual errors. If we want to do that, we're going to square the equation itself, which is always equal to a residual because we're doing an approximation on this. So if I have a set of data point and I run a linear regression through this, I'll get a line where I, in essence, minimize the error of that line to that particular point. And I do it collectively over all the points. If I were to run this with a linear interpolation, then I would get something as a profile that would look like this. If I did something like a cubic, I would get that. Where in actuality, I want something that would look like this. This might be associated with manufacturing error or tolerances or whatever, where I really don't want some sort of pattern that's going to oscillate and go through all the data points. What you do is to differentiate the error with respect to the coefficients. If I'm doing a linear, I have 2 coefficients, A0, A1. If I wanted to do this at higher order, how many equations? For a quadratic? 3. Right, so I'd have A0, A1, A2. So this is the general form of the equation that you're doing. And to minimize these, you set the derivatives equal to what? 0. Right? So you wind up, that's what these are here. So you wind up with these expressions. Now the summations mean that I'm going to sum over all the data points. So I wind up with a set of equations. In this case, it really turns out to be a 2x2 matrix. If I'm doing a linear regression, I suggest that if you can solve it as a 2x2 matrix for the unknowns, the A0, A1, it's really quick. Or you can go through and plug in all these coefficients, all that sort of stuff, and then try to work it out. I know that there's a formula that I gave you for this for A1, A0. I don't know if you necessarily want to memorize that, but if you can do it as a matrix, then you've got it for as high an order as you want to go. So you can solve a 2x2, it's easy enough, 2 equations, 2 unknowns, or you can solve a 3x3 or a 4x4 or what have you. Actually, there's a good example in the notes, I think, that I went through before, and also in your textbook. So if I have a bunch of data points like this, what I'm doing is, in essence, setting up tables where I'm evaluating these products that you see. Calculate the mean. It's the first thing I do for X and Y for the data sets. Now I find A0 and A1. Now if I want to use the formula, if I memorize that, then I can find A1. And then A0 is very simply the y bar minus this thing. So there's my equation. Now I think you've been through matrices, so you can, if you do it as a 2x2, you won't have to memorize these kinds of equations. What happens is you'll wind up fitting a line through the set of data. If you get a bunch of data points that look like this, and you're putting a linear regression through it, I would be somewhat suspicious. How do you tell if this thing is any good or not, aside from doing it visually? Correlation, right? Now, I don't expect you to memorize the correlation coefficient, but basically you can tell visually if this thing should be a higher order or not. So this is what we mean by minimizing the error between the measurement and that regression line. So here's one in which we have very good regression, and one in which it's probably not so good. But it's still pretty good as far as giving a trend with regards to what the data is. This is if you wanted to find the correlation coefficient. I don't ask you to memorize that, it's just too long. But just remember, if I were to say, how would you know if the data was, or the curve that you generated was any good? You could say, I would run a regression, or a correlation coefficient calculation. There's a table in the back of the textbook that has these various methods in there. Now these you've been through before. The one that I just include here was the linear regression. So there's the formula for that regression, and then the errors that are associated. In the Monte Carlo simulation, one of the homework problems that you had, basically you're doing this as a random or stochastic approach. So you're balancing it between usually a -1 and 1 or 0 and 1 or whatever the ranges are as far as your random number generator. You wind up creating then a series of solutions. It's called Monte Carlo because it's based on the Monte Carlo gaming approach. So it uses random numbers to generate these processes, and they're used in all kinds of different type of problems. I won't ask you to work through a Monte Carlo. I mean, how are you going to do that unless you're the random number generator yourself? But I would say, if it comes up as a definition, I may ask, what method would you use to do nuclear decay? Or what's a method that would allow me to account for variability, Brownian motion, particle diffusion in a room? Monte Carlo. Basic forms of PDEs. Be sure that you can do the degree and the order. This is a transport equation. That's what order? Second order. Why? Because of the second derivative. What's the degree? First. What's this one? Second order. What's this one?
Second order.
What degree?
Two. First degree. Oh, wait, first, that's right.
It's always the derivative to the highest order. That is a second order equation. The degree on that is 1. You have 3 choices in classifying equations: parabolic, hyperbolic, and elliptic. The 1D wave equation, what type of equation is that? You got 1 of 3 choices.
Parabolic.
I got 1 parabolic, I got 1 hyperbolic. That means the rest of you think it's elliptic? There's no abstention. Wave equations that look like this are always hyperbolic.
In your face, Will.
Hyperbolic. Here's the heat equation. What type of equation is this?
Parabolic.
Parabolic. It's a marching in time. Laplace equation. What kind of equation? Elliptic. What's the difference if I move this over to the left-hand side? What does the sign become?
Negative.
Negative. That's how you can tell the difference between elliptic and hyperbolic. If there's a negative sign, hyperbolic. How about this equation? Poisson's equation. It's elliptic. This is what you had in calculus. This little formula. So you've got the coefficients setting on these higher derivatives, the second order derivatives. Go down to these little equations, right? Remember what that equation is? Harmonic.
Which one?
Remember the square root of b squared minus 4ac? Finding the root plus or minus b in this thing? All right, that's all that is. So that's how you can determine if you have a series of equations in there, whether it's elliptic, parabolic, or hyperbolic. But the little rule of thumb that I just gave you on the previous slide should be sufficient. But just in case, you can always go back to your calculus. This is a general transport equation with regards to any variable, whether it's a scalar or a vector or what have you. Now the G means dot, so it means times. So here's a first derivative term, here's a second derivative term, a source or sink term, a time derivative term. Phi is the unknown variable. K is a diffusion coefficient or a thermal conductivity or what have you, and that would be the source and sink term. If you can look at that equation and set up a discretization of that equation, that holds for almost any equation that you're going to deal with in engineering or science. The finite difference method. It's based on what particular technique? Taylor series. Second order accuracy is a central difference. First order accuracy would be a one-sided forward or backward difference. In discretizing equations like that, you generally want to try to keep them second order accurate, which means a central difference. These things are easy to set up when you see a derivative, whether it be first or second order. You should, by now, be able to write down what that discretization would look like. If I have an equation, an elliptic equation that looks like this, I do second order approximation. That derivative will look like this. You notice I'm using double indices for the subscripts for node points. So here's the second derivative with respect to x, the second derivative with respect to y. There's the source sink term. Now these are the remainders, right? So that would be the error associated with that particular discretization. Here's a second order equation. If I do a finite difference on this, here is my central difference for the second derivative term, my central difference for the first derivative term, and then I would evaluate that at the node point I, the one that I'm solving for. If I go to a finite volume, what am I doing? Remember, I'm integrating over the volume that surrounds each point. And I'm going from I minus 1/2 to I plus 1/2. Those denote the faces of the control volumes. The only difference in this particular technique is when you get done, is how you handle this term right here, the integral of phi dx. Here it's a point discretization. Here it's an integral, and I happen to use 1/3 Simpson's rule, or any rule that I want with regards to integration. If I'm doing an iteration, that is something that is steady state, I will want to use something that will accelerate that solution as quickly as possible. This is the Gauss-Seidel method with relaxation, which makes it a successive over relaxation if that value is between 1 and 2. If it's less than that, if it's between 0 and 1, it's under relaxation. But if I have a problem that I want to accelerate to steady state, to a converged solution as quickly as possible using an iteration, I will do this particular technique. That is the most preferred method. And that comes from that discretization that you just saw for that Poisson equation. If I have a time-dependent term, I will generally want to use an ADI method. Now, in this particular technique, this is steady state. I can still use an ADI for steady state, although I would prefer to do the SOR. But if I have a transient term, I will want to do this as an ADI, alternating direction implicit. So if you remember, in an ADI method, it is tridiagonal. That means there are 3 unknowns on the left-hand side, and everything else is on the right-hand side. So here are the 3 unknowns in the x direction, denoted by the asterisk. That means the first step. In the second step, this would be the sweep in the y direction. They're also unknown. Now I'm going in the y direction, and I've taken all these things and moved them over here. That's called the ADI method. Everybody understand?
Yes.
All right. Okay.
You know,
If I look at this equation, how am I solving it right now?